Good morning, everyone. My name is Sneha, and I am doing my PhD from University of Technology. And today I'm going to present on the topic process and evaluation of ultra high performance hybrid fiber reinforced concrete with weighted fiber percentage. I will introduce the topic with the motivation and the application, and the problem statement and the development design, and the experimental outcomes, and the so basically, concrete development with the concrete is very progressive, but with the advancement, we need advanced materials with toughness and durability and durability characteristics. So to serve that purpose, we have ultra high performance.
Please keep snapping.
So, good morning, everyone. My name is Sneha, and I'm doing my PhD from the Institute of Technology, Roorkee. And today I'm going to present on the topic factor process zone evaluation of ultra high performance hybrid fiber reinforced concrete with varying fiber percentage. And this is the outline. I will be introducing the motivation and the application of this material, and the problem statement, and the development design, and the experimental outcomes, and the conclusion. So basically, the development in the field of concrete is progressive, but with the advancement, we need advanced material that improve the toughness and durability and durability characteristics of the material. But so to do that, we have ultra high performance concrete, which is emerging as a future of construction material because of its superior structural properties of high compressive strength of greater than 120 MPa and greater tensile strength of 6 MPa. And these all are happening because of the micro fine dense packing in this material, which leads to the reduced porosity, and it leads to more durable structure. And as far as the ductility is concerned, the fibers are the most important part in this study. The fibers are the one that will improve the toughness, and that will improve the brittleness of the material and improve the toughness, as you can see here. Without fiber, there is a brittle behavior, but with fiber, the post-cracking behavior is significantly improved. And so in this study, we are focusing on how this varying percentage fiber will affect the post-cracking profile of the material. So these are the construction that has happened worldwide with the gaining a lot of traction these days. So this is my problem statement. So first we will be discussing the developed design for this material and the mechanical property evaluation, and then fracture characteristics with the varying fiber, how it is affecting with the monotonic loading under center point bend load, and then analysis of the post-cracking behavior. So these are the materials that are used to develop this mix, with this high mix, and usually in UHPC the requirement for cementitious content is very high. So in order to reduce the consumption of the cement, we have used this alternative and replace the cement with the other cementitious material like microsilica and ground granulated blast furnace slag in different proportions, so that these microfine particles will help to fit in the micropores and densify the mix, and without compromising its strength, it will fill the pores. And additionally, we have used the fine silica sand in different mesh size to again give a dense packing to the structure. And we have used the straight steel fibers of aspect ratio of 100 to 20 mm length and 0.2 mm diameter. So we have used this shear pan mixture to come up with the consistent flowable mix. With the flowability, we are getting 30 mm on the slump table, and we have used the cylinder as well as tube specimens to determine the compressive strength, and for elastic modulus we have used the cylindrical specimens as well. And this is the composition of my mix, and from this mix I have got the strength of 126 MPa and modulus plasticity of 44.5. So now, in order to see the fracture properties and the fracture behavior, we have casted the beams in 3 different categories to study the post-cracking behavior under fracture. So first set we have used the 2% fiber with the 20 mm length, and in second set we have used 2% fiber but with high-grade combination of 20 mm fiber 1.5% and 13 mm fiber 0.5%. And recently we have used 1.5 with 20 fiber, and this is the cross section that we have used for the beam for flexure testing. And we have done all the testing in the BISS 500 kilonewton per T test machine. We have used 12 mm flip gauge, and it is done all the testing is done in COD controlled loading rate. So these are the results that we have got from the load CMOT. As you can see, the fiber percentage variation is affecting the post cracking profile significantly, which infer that crack length and crack fiber volume has greater influence on this. And the flexure and the factor energy is also higher for 2%. And the main reason is for that we have, for the crack resistance, we have more number of fiber engaged in the crack bridging action for the 2%. But to get the details of the crack and everything, as we see the results of DIC, we will able to comment on the mechanism that is happening behind. So to do that, we have used the DIC results. And as we know, as the deformation process, the specimen changes, deformation changes with the specimen as the loading progress, and factor process zone is continuously developing. So in order to observe the appearance and the propagation of the factor process zone, we have divided the post and pre and post peak profile into different segments. First is the LOP point, and then we have a pre-peak MOR at 90%, and this is the MOR point, and this is the 80% of the post-peak MOR, and E is the 50% post-peak MOR, and this is 30%. And this small E1, E2 can be to the left or right, depending on the fiber volume. And F1, F2 is the point representing the crack with the LF/3 crack. So, and the results of hybrid fiber volume are also interesting to see that we can see the crack branching as well in this, because initially the starting stage the crack was propagating from here, but after the crack was peak toward the peak, it start propagating from this, and finally it branched and then into the common crack propagation. So the DIC results are also in good correlation with the experimental. We have done the validation as well. So if we correlate these results with crack width and crack opening, we can see that it is interesting to note that in the load CMOT, the 2% results are higher peaks and higher peaks. But as far as the crack length and crack width are concerned, we have lesser crack width, crack length, and crack width in case of hybrid combination. Because in hybrid combination, there is a dual scale mechanism that is happening. It's like short fiber are working in the initial stage to bridge the micro cracks, but as the crack propagates and the bigger, larger fibers will come into the picture, because and small fiber length also help to suppress the crack propagation, and that dense barrier that is making with the help of micro and with the short and long fiber will help to delay the crack propagation. So this all outcomes are visible in these results, and from the acoustic emission results also this is quite quite visible. Like in 2%, the acoustic energy we have. This is the combined plot actually with the load versus time from the test machine and the cumulative energy versus time from the acoustic energy result. So acoustic energy is also showing the favorable results for the hybrid as well, because hybrid fibers are, and it is showing that hybrid fibers are engaged in overall improving the performance of the material. And if we see the mode of cracking, mostly the cracking is in the tensile. To define the mode of cracking, we have right angle versus average frequency plot. So majorly the cracks are in tensile, but as we proceed from 2% to 1.5%, little bit shear cracks are increasing. The main reason is that if we, that when we have 2% fiber, because of increased content of matrix and the fiber has close bonding, so it will not lead to the. It has a greater contact between the two crack surface, so it has the ability to bridge it and not lead to the shear cracking. And so if we conclude my work that if we just see the load CMOD results, we can say that 2% fiber are behaving good. But if we are concerned about the crack mechanism, crack propagation, where crack length and width are important, and we don't want the crack to be wide open very easily, we have to go for the hybrid combination, and it is performing better in as the way the crack is propagating in the material. So, and these are my thank you for the session.